Hi everybody, welcome back to the Feynman Technique. So today we're going to be developing a nice formula for the gamma function. Now, the gamma function is the analytic extension of the factorial. In other words, it allows you to quote unquote find the value of things like 1/2 factorial or negative 1/2 factorial. Of course, we know that factorial is only defined for positive integers. Um, the gamma function is defined for more values, even complex values. But anyway, let's get into it. So we're going to begin with the simplest case, the integral from 0 to infinity of e to the negative tx dx, which easily evaluates to 1 over t. All right, so we'll keep that in mind. So our I of t is equal to 1 over t, and it's also equal to that integral. Okay, so next we're going to use the Leibniz rule for differentiation under the integral sign to take a derivative on both sides of our equation right here. We have this is equal to 1 over t, and we will take a derivative on both sides, giving us this. So you'll notice we recovered a negative sign in both cases. All right. And then we can do it again. If we differentiate again, you'll see we'll get rid of the negative signs. Will both cancel. We'll get another power of x on this side due to differentiating e to the negative tx with respect to t, and we will this will be what we get on the right hand side. Let's do it one more time. We're going to differentiate one more time. We're going to take this and differentiate it with respect to t again. And what do you think is going to happen? This is going to increase by 1. We're going to get a factor of 3 down here, and this will decrease by 1. That's what's going to happen every time. So you'll note this is what happens if we get it again. Now, take a look at this. This pattern is going to continue. Every single time we do this, what's going to happen is we're going to recover another negative sign, which will cancel on both sides. And every time, you'll notice every time we differentiate, we recover the next integer up. So we're just going to end up getting the product of a bunch of successive integers. In other words, we're going to get a factorial on the right-hand side. So here's the pattern. If you take the integral from 0 to infinity of x to the n e to the negative tx dx, this is what you end up getting. You always get n factorial over t to the n plus 1. Now, what about... Now, the reason we need the gamma function is so that we can extend this to non-integer values. So that's why we defined gamma of n plus 1 to be n factorial. So now we have this formula. The integral from 0 to infinity of x to the n e to the negative tx dx is gamma of n plus 1 over t to the n plus 1. Now, this is not the standard way it's written. Normally, what you would say is you would rewrite this integral as the integral from 0 to infinity of x to the n minus 1, and then have it equal gamma of n over t to the n. Anyway, guys, I hope you enjoyed that, and we will see you next time.